All right, today we are diving into one of the fastest, most powerful tools a programmer has for talking between programs, System V Shared Memory. You know, if you've ever found yourself needing two different processes to sling massive amounts of data back and forth at just, ridiculous speeds, we're talking high-frequency trading, real-time video processing, that kind of stuff, then this is the tool you absolutely need to get.
So that's the big question, right? You've got two separate programs and they need to communicate. But not just the little hello, they need to share huge chunks of information, and they need to do it without bringing the entire system to its knees. How do you pull that off? Well, the secret is to get the middleman out of the way.
And this slide just lays it out perfectly. See, most of the time when programs talk, they use the operating system's kernel as a kind of courier. One program bundles up its data, hands it to the kernel, and the kernel then goes and delivers it to the other program. It works, it's safe, but it's also kind of slow. Shared memory, that's the express lane. It's like carving out a piece of RAM that multiple programs can see and touch directly, as if it were their own. No copies, no waiting for the kernel to make deliveries, it's just there.
So here's our game plan for today. First, we're going to talk about what makes this so incredibly fast. Then we'll walk through the whole life cycle, how to create it, how to actually use it, and maybe most importantly, how to clean it up properly. And we're going to finish with the one single rule that you absolutely positively cannot afford to break when you're using this stuff.
Okay, let's get right to it. The main event, why is this the undisputed speed champion of inter-process communication, or IPC?
The absolute best way to picture this is to imagine a secret whiteboard. Let's say you and your buddy are in totally separate, sealed-off rooms. Now, instead of passing notes back and forth through a slow messenger, what if you could both just reach out and draw on the exact same whiteboard, one that magically exists in both rooms at the same time? That's shared memory. A change one program makes is instantly visible to the other. No delay.
So, how do we get one of these magical whiteboards? Well, it's not as complicated as you might think. It's basically a two-step dance to tell the operating system, hey, I need a shared space, please.
First things first, we need a unique name for our whiteboard, something everything on the system can recognize. That's what ftalky, or file to key, is for. It generates this special key. Then we take that key and we go to the OS with the shmget function. We're basically saying, hey OS, see this key? I need a shared memory segment tied to it, and I'd like it to be, this many bytes.
In this key, it's not just some random number, it's a system-wide identifier. Any program that uses the same file path and ID for ftalk is going to get the exact same key. It's the shared secret that lets completely separate programs find the same room where our whiteboard is waiting. So if the key from ftalk gets us into the right room, shmget gives us back a shimid, or shared memory identifier. Think of this as the specific ticket for our whiteboard inside that room. From here on out, we use this little integer handle for everything we want to do with that specific piece of memory.
Okay, so we reserve the space with the system, but our program still can't actually see it or use it. The next step is to attach it, to bring it into our world so we can finally start writing on that whiteboard.
And this is the magic moment. We use the shmat call, that's for shared memory attach. We hand it our shmid ticket, and the operating system literally maps that segment of memory right into our program's own address space. It's like the whiteboard just materializes right in front of us.
And here's the really beautiful part for us coders. After all that setup with keys and IDs, what do we get back? A simple pointer. That's it, a plain old memory address. From this point on, you just treat it like any other piece of memory. You can read from it, you can write to it. All the behind-the-scenes complexity is totally hidden. All you've got is a pointer to your whiteboard.
Now, playing with our shared memory is awesome, but just like any powerful tool, we've got to be responsible and clean up when we're done. And honestly, this is where a ton of bugs and confusion can sneak in if you're not careful.
Let's go right back to our analogy. When your program is finished using the whiteboard, you can do one of two things. You can just leave the room. The whiteboard is still there, and anyone else with the key can still come in and use it. Or you could be the person who tells the janitor, hey, we're all done here, you can get rid of this whiteboard. Those are two very, very different actions. So this is the thing you've got to get right, the difference between shmdt and shmctl. Shmdt is you detaching. You're unplugging the memory from your program. You're leaving the room. But the memory itself, the whiteboard, is still there. shmctl with the IPC RMID flag, that's you telling the system, hey, this thing can be deleted now.
The OS is smart. It'll wait until the very last person detaches before it actually erases it, but you've marked it for destruction. If you forget this part, you get memory leaks that stick around until the whole machine is rebooted. Not good.
All right, we've covered the power, we've covered the process, but now we have to talk about the responsibility. There is one huge, critical, unseen danger that you absolutely have to respect, or things will go very, very wrong.
And this right here, this is it. This is the single most important sentence to burn into your brain. The operating system gives you this amazing shared space, this whiteboard, but it gives you zero rules, no referee. It doesn't tell you who can write or when or how to take turns. It is a complete free-for-all.
Which of course leads to the big, scary question. What happens if two programs try to write on the exact same spot of that whiteboard at the exact same millisecond?
The answer is simple: total chaos. You get what are called race conditions, where the final state of your data just depends on who happened to win the race to write last. This means corrupted data, just bizarre, unpredictable behavior that you can't reproduce, and yeah, very often program crashes that are an absolute nightmare to try and debug.
So what this means is you have to bring your own traffic cop to the party. You must use other tools like semaphores or mutexes to manage access. These are basically like a talking stick, only the process holding the stick is allowed to write to the shared memory at any given moment. Shared memory gives you the speed, but these synchronization tools give you the safety. They are not optional.
Okay, so let's wrap this up. What are the big takeaways? Number 1, shared memory is the fastest way for processes to communicate because you're cutting out the kernel and accessing memory directly. Number 2, remember the life cycle. You get a key and an ID, you attach, and when you're done, you detach and you tell the system to remove it. And number 3, the most crucial point of all, you are 100% responsible for providing your own synchronization. It's not built in.
And really, that's the core trade-off here, isn't it? SystemV Shared Memory hands you the keys to an incredibly high-performance machine, but it also trusts you completely to be the one to drive it safely. So the real question is, now that you've unlocked all that speed, can you handle the responsibility that comes with it?